So next talk is by Justin McInroy about introduction to Axial algebras. So please, floor is yours.
Okay, thank you very much for that introduction. Yes, I'm going to give a course on axial algebras. My idea for this is to introduce the subject to you. I'm going to begin with a bit of motivation or history to the subject. And then I'm going to give you the definitions and things. I'm going to move through the definitions of the algebra, how you associate a group to the algebra, a naturally associated group, and that's going to be very important for us. I'm going to say something about ideals in the algebra and perhaps some decompositions. And then in the latter part of the course, I'll move on to some more recent topics, recent topics, I think. Okay, so as I say, I wanted to begin with, oh, excuse me, I've got a bit of a sore throat today, so we'll see how well I last through this hour. Yeah, so I wanted to begin with a bit of motivation and perhaps history of where axial algebras came from. And so let's see if this works okay. Motivation, lovely. So the first bit of motivation comes from vertex operator algebras. So these are vertex operator algebras. So these were first considered by physicists. So first considered so I guess before I go on, I should also say I'm writing some notes alongside this. So what I'm writing here will be available, but I've also got some proper LaTeX notes, which are evolving as the week goes on. Okay, so VOAs, so yes, they're first considered by physicists, and this is to do with things like chiral algebras or 2D conformal field theory, but perhaps mathematicians are most interested in them because of the links with monstrous moonshine. And so what is this? So there is a certain VOA called V natural, and this thing was the object which was used to in Borchard's proof of the monstrous moonshine conjecture. So roughly speaking, this says that you have the monster simple sporadic group, and you're looking at various irreducible modules for that, and the dimensions of these irreducible modules. And it was noticed that the numbers, these dimensions, the numbers which come up, are also numbers which come up in number theory, in the J function. And so originally this was not very well understood at all. I'd still argue that it's very difficult to understand, it's quite opaque, but this object, V natural, this VOA, this is the thing which Borchard's used to prove monstrous moonshine, i.e. the link between these numbers which come up in the J function and these irreducible modules for the monster. So this thing is a VOA, and its automorphism group is indeed the monster. So I guess I should also say the monster is the largest simple sporadic group. So I'm going to say a bit more in a minute about those. Incidentally, if you can't read my writing or you need me to say something again, please, or if I haven't explained anything well, please say something and I will say again. Okay, so I don't really want to tell you what a VOA is. It's quite a difficult object, but I'll give you a brief idea. So roughly speaking, a VOA is an infinite dimensional vector space, but it has a number of finite graded pieces. So it basically looks like a direct sum over say positive numbers of some VI, where the VI, maybe I'll say, where the dimension of the VI are finite, and there are infinitely many different products. And these different products, they all respect this grading, but they all respect it in a slightly different way. So for instance, the, let me get this right, the nth product will send, if you take the nth product of an ith piece and a jth piece, it sends it to something like the I plus j plus n minus 2th graded piece. It's something like that anyway. So the piece that it sends it to depends on the grading of the first two pieces and on the particular product you use. So they're all linked in this quite intricate way. And as I say, our main example here, or the one which is the motivation for axial algebras, is this moonshine VOA. Which is V natural, and in this, V0 is just a copy of the field. Perhaps I'll just say is one-dimensional. V1 is 0, i.e. it's just zero-dimensional vector space. And V2 is the Griess algebra. So for those of you who don't know, the Griess algebra is how the monster simple sporadic group was first defined. It was defined by Griess as the automorphism group of this algebra he introduced, which he originally called the friendly giant, but we now know, or we now call the Griess algebra. So this is 883 dimensional algebra. And this algebra is commutative and non-associative. So in particular, here we're interested in this non-associative bit. So this is how the non-associativity gets into axial algebras, as it were, or at least we'll see in a minute that we have generalized from this. And as I also said up here, the important bit about the moonshine VOA is that its automorphism group is the monster. Okay, so that's one source of motivation. We have these VOAs, and they were first considered by physicists, but then there's this lovely link with monstrous moonshine here between some slightly or very different areas of mathematics, and hence we want to better understand this link. As I said, VOAs are rather complicated objects, so we want a better way to understand them. And one of the first attempts at this, or ways to do this, are Majorana algebras. So these were introduced by Sasha Ivanov. Maybe 15 and a bit years ago, something like that. And if you like, they are the predecessors to axial algebras. So Majorana algebras are examples of axial algebras. But axial algebras are a slightly more general type of algebra. And so what were they introduced for? Well, they were introduced to generalize, some properties which were observed, which were seen in both the moonshine VOA and the Griess algebra. Okay, so what were these properties? Well, originally Norton observed for the Griess algebra that there existed some idempotents which he called 2A axes. And the reason why they're called 2A axes is because these idempotents are in bijection with some involutions in the automorphism group. So involutions are elements of order 2. So just a group element of order 2. So they're in bijection with some involutions in the automorphism group of, I haven't given it a name, so let's call the Griess algebra A for the minute. And the automorphism group of the Griess algebra is the monster. And so you've got these bijection between these these idempotents and these involutions in the monster, and the involutions happen to be in the conjugacy class, which are called 2A. Hence, we call these things 2A axes. So we're in bijection with involutions in the monster, in the conjugacy class, (2A). Okay, well, they have some other properties as well. So if you take an axis, one of these 2A axes, and you look at the, let me say some other things here. So we will see these in a lot more concrete form in a minute. So each 2A axis is, let's say, has eigenvalues. So I'm thinking about its adjoint action on the algebra. So it has eigenvalues 1, 0, a quarter, and 1/32. It is semi-simple, so it decomposes the algebra as a direct sum of these eigenspaces. And moreover, the eigenvalues in these eigenspaces multiply in a restricted way. So I'll be more precise about that in a minute. Or of eigenvectors, sorry. If I said eigenvalues, multiplication of eigenvectors is restricted. So it's not only that we've got this bijection, we seem to have a bijection where these idempotents are important elements of the algebra, and these involutions that we get here, these involutions preserve this decomposition into eigenspaces, and moreover, actually preserve this multiplication. So the associated involution preserves, I'm just going to write this at the moment, which is not very explicit, but I will be totally explicit about what I mean shortly. Okay, so that is what happens in the Griess algebra. But I said also that it generalized some properties seen in this VOA. Well, I've already said that the Griess algebra is one of the graded pieces of the VOA. So in particular, it's this 2-graded piece. But actually, a little bit more than that. So this is what Miyamoto observed. Sorry, it should be Miyamoto. So Miyamoto observed similar properties in this moonshine VOA. So here, there are these things called easing vectors. So this is ISING, easing vectors. So these things aren't quite idempotents because we have several different products, but they are, at least for the weight 2 part, they are scaled versions of idempotents. So, okay, so scaled versions of idempotents, sorry, with respect to, actually, I should have said it's with respect to the -1 product. Let me say, with respect to the -1 product. And these easing vectors live in the weight 2 part. And remember, the weight 2 part is the Griess algebra. So these eigenvectors are just scaled versions of the 2A axes, which Norton observed. And similarly, so they have this nice decomposition. Moreover here, they don't just preserve the decomposition with respect to this -1 part, they preserve a lot more of the VOA structure. And again, there's this, this naturally associated involution. So these are in bijection with involutions in the monster, which is, as I say, the automorphism group of this VOA. So in particular, you're seeing here this nice structure that we saw for the Griess algebra, where we have this bijection between things that we're going to call axes, idempotents that we're going to call axes, and these involutions, which preserve some sort of nice algebraic properties and also some nice group theoretic properties. We see a similar type thing here. So I've been much less explicit about what it is here, but my claim is that there is also this bijection. What Miyamoto showed is there's also this bijection between certain elements and these involutions. And really, this is what Majorana algebras were designed to do, to capture this, this bijection between these things and these nice properties. And this is also what axial algebras do. Okay, so I want to give a little bit more motivation, but some more, by way of some more examples here. So my next bit of motivation are Jordan algebras. And these were originally introduced to study observables in physics or in quantum mechanics. And these were introduced in 1933 or something like that. And they are non-associative algebras which satisfy the Jordan identity. Which is that if you take two elements, x and y, if I multiply x and y, and I multiply that with the multiplication of x with x, then this should be equal to doing this same thing, but with the brackets in a different order. So instead, I will start with x times x, and I'm going to multiply that by y. And then after that, I'm going to multiply that by x. So I've just reordered my brackets here. And this should be true for all x and y in my algebra. And it's well known that idempotents in Jordan algebras are semi-simple, and their adjoint, the adjoint action of the idempotent, has eigenvalues have, I think that should be, and have eigenvalues 1, 0, and a half. And moreover, it's well known that the multiplication of the eigenvectors for these eigenvalues is restricted. And in fact, Jordan algebras turn out to be examples of axial algebras. This isn't always true, but it's true whenever there are enough idempotents in the algebra to generate the whole algebra. So if there are enough idempotents, i.e. the algebra, the Jordan algebra is what we're talking about, the Jordan algebra can be generated by idempotents, then it is an axial algebra. Okay, I might say this a bit more quickly now. There are things called Matsuo algebras. That's meant to be an O on the end there. Matsuo algebras. And these are non-associative algebras defined from, well, strictly speaking, they're defined from a Fisher space. But you can actually think of them as being defined from a 3 transposition group. In a very concrete way. So I'm going to give this as an example either later today or maybe tomorrow. And a 3 transposition group is just a group G with a normal set of involutions that's my calendar telling me I've got things to do. A normal set of involutions, I've called it N here. Okay, that just means that it's closed under conjugation by the group, such that the order of the product of any 2 of these is either 1, 2, or 3 for one of my involutions. There can be other products in the group, other product orders in the group, but for the involutions, you multiply those. These are the only product orders you can get. So that's what a 3 transposition group is, and directly from a 3 transposition group, you can define an algebra. And conversely, it turns out that from the algebra, you can associate a 3 transposition group. So they're really in one-to-one correspondence. And here, examples of 3 transposition groups include various symplectic, orthogonal group and unitary groups in characteristics 2 and sometimes 3. Also the Fisher sporadic groups. This is how they were originally found, actually. I mean, Fisher was looking to classify, well, yes, he was classifying 3 transposition groups, and he found these sporadic groups. And some other groups here, ... So actually, we know all 3 transposition groups. These were classified by, by John Hall and Hans Kuipers. Oh, well, originally there was a full classification given of, the first classification was by Fisher, and this was not counting the center or modulo the center, and then John Hall and Hans Kuipers, I think, gave a more full definition, a more full classification, sorry. Okay, so those are Matsuo algebras, and all Matsuo algebras are axial algebras. And I guess I want to say 3 other things here by way of motivation. So the first is about finite simple groups. So we've already seen that there are a number of different groups occur. So we've seen the monster sporadic group, we've seen these other Fisher sporadic groups, and we've seen 3 transposition groups, a number of which are simple groups. Jordan algebras, the automorphism groups of those have among them some finite simple groups as well. So axial algebras are allowing us to see all of these different finite simple groups in the same framework. So we have seen various different groups or simple groups as automorphism groups, and axial algebras are allowing us to see these in the same framework. Including sporadic and non-sporadic examples. So I should also say that there's also a paper by Tom de Metz and Michiel van Kouwenberger, which shows that you can get some simply laced groups of Lie type. So groups of Lie type which are simply laced diagram. These are those with diagram A, D, or E. So these groups you can also see as automorphism groups of axial algebras. So there's some more here as well in my list of various different groups. And so, well, one hope in this area is that this allows us to see the classification of finite simple groups in a different way. So we don't know that we can get all of the groups yet, but we can at least see some of them. And perhaps this allows us to view this in a different way. Currently, you know, each different group will have a different type of construction. And this is a construction which allows us to see them in the same framework. So that is maybe very sort of high level goal motivation. Perhaps more concretely, two other things briefly, is that axial algebras have been seen in PDEs. So Tkachev has found examples of axial algebras in the theory of nonlinear PDEs. And these are things called Siang algebras. And here, idempotents have eigenvalues 1, -1, -0.5, and 0.5. And finally, algebras of vector flows on manifolds. So here, Fox he hasn't quite identified axial algebras, but he has speculated some axial type behavior. Okay, so I have said quite a lot about motivation here, and I haven't told you what axial algebras actually are. So I should probably get on and do that. Okay, so what are axial algebras? So I said all the time in the motivation, I was saying that there's this restricted multiplication of eigenvectors. And to make that more precise, I need a gadget. And the gadget I'm going to need is called a fusion law. So that's the first thing that I want to say something about. So this is, so this allows us to be rigorous about what I've just been saying is this restricted multiplication. Okay, so definition. A fusion law, I'm going to write script F. And this is going to be really, it's going to be a pair. Script F. So where is a set non-empty set F together with a symmetric binary operation. So this is my star, so that takes something from F cross F and it maps it into this, where by this I just mean the set of subsets of F. And so this is what a fusion law is. So, so what's an example? Well, an example of this, I'm going to write it in a table because it's a binary operation. Let's suppose I have 1, 0, and eta. One times 1 is going to be 1. 0 times 0 is going to be 0. 1 times eta is going to be eta. 0 times eta is eta. Eta times eta is going to be 1 and 0. And this is symmetric. So I'm going to fill these out. And there I've left empty spaces. So my, I guess, notation here, or my conventions for these writing these tables, is that I'm going to not write brackets, because that will make my table look a bit too messy, and a blank space means the empty set. So for example, from this table, 1 star 0 is the empty set. 1 star eta is the set which contains eta. 1 star eta is there, and eta star eta is the set which contains 1 and 0. So this is an example of my fusion law. And in fact, if eta is a half here, this is the fusion law which Jordan algebras satisfy. So I said that Jordan algebras were examples, and this is the fusion law which they satisfy. I'll give you one other quick example. I should just say that this is called Jordan. For that reason, we call this a Jordan type eta. So it's the fusion law of Jordan type eta. So my other example, my second example, is going to be have 1, 0, alpha, and beta. And the first part of the law is going to look the same. This upper half, that's just an eta type, a Jordan type eta fusion law. And then I'm going to complete it in these places by having betas here. And finally here, I'm going to have 1, 0, and alpha. And this is going to be called a monster type law. And I'm going to write this maybe as M alpha beta. And sometimes I'm going to say generalized here, although sometimes I might leave that out. And as you might guess, the Griess algebra satisfies the fusion law with M a quarter 1 over 32. So this is why we have this name for this law. So there are a couple of examples, and the one other thing I wanted to say here is I have one other notational convenience, which is that if S and T are subsets of F, I'm going to write S star T, and all I mean by that is the union over all S in S and T in T of S star T. So this is just extending my binary operation to subsets rather than elements of my fusion law. Okay, so that's all I want to say about fusion laws for the minute. And I can just about tell you what an axial algebra is before we finish. So I guess recall that the adjoint map is the map which takes some vector to A times that vector. So for a certain element A, I'm going to again, I'm going to write A lambda of A is going to be the lambda eigenspace for the adjoint action. And where the A is clear here, I might just drop it. And also recall that some certain A in my algebra is called semi-simple if the adjoint is diagonalizable and of course, what does this mean? That means that my A decomposes as a direct sum of eigenspaces, and I'm going to write spec A for the eigenvalues of the adjoint. And so I'm going to define, rather than just writing A sub lambda, if I write A sub some subset, that's going to mean just the direct sum over all of those lambdas. This is again going to be my shorthand. So with those in mind, let F be a fusion law an element A in some algebra is an f-axis if, firstly, I want that A is an idempotent The second thing is that I want A to be semi-simple. So an idempotent, remember, means that the element squares to itself. Being semi-simple, this just means that precisely this, that the sum over all the eigenvalues is the whole algebra. And finally, I want that all of the eigenvalues are contained in my fusion law, and this is the multiplication being restricted step. So if I multiply two eigenvectors, let me be explicit here for a minute and not miss these out. If I multiply a lambda eigenvector by a mu eigenvector, then their product should lie in the product of the, let me move this a little bit for you. And this is by definition my shorthand for the sum over all eigenvectors, the sum over all of these mu's, which are in the fusion law. Sorry, not eigenvectors, eigenvalues. The sum over all these eigenvalues, which are in lambda star mu in the fusion law. So this gives me a way to control my multiplication. So this is what an axis is. And as I'm really running out of time here, let me just, I have a few more things to say on this, but let me just say an axial algebra, it's really a pair, I'm just going to often write A, but it's really a pair A comma X, where A is a commutative, non-associative algebra and X is a set of axes, a set of F axes I'm often going to drop these Fs where they are clear. So I'm used to writing an axial algebra rather than an F axial algebra. But let me be very explicit here. So an F axial algebra is a commutative non-associative algebra, and X is a set of F axes such that, or let me just say, which generate the algebra. So I think that's me just about out of time here, but let me say that, so everything I was saying before, we've now seen explicitly what an axis is, and this is what I was saying before was these nice properties which were seen in the Griess algebra, and very similar to what was seen in VOAs. So we've got an idempotent, we have the fact that it decomposes the algebra nicely, i.e. it's semi-simple, and we've got this restricted multiplication, and then we need enough of these that they generate the whole of the algebra. So this is saying that we've got a set X of them, all for the same fusion law, and they generate the whole algebra. And this is what we see in the Griess algebra. This is what we see in a lot of Jordan algebras, and also many of these other algebras. So next time I will be, I'll be a little bit more explicit about, or I've got a few more comments to make about the definition here, but the main thing I want to get to next time is, I was saying in the motivation that there was this bijection between these idempotents, which we now are going to call axes, and certain elements of the automorphism group. And that's the thing that I want to talk about next time. Okay, that's it for me today. Thank you.
Thank you for the presenter. Any questions, please? Questions? I have one question. Is it possible to study this stuff with topological stuff? Can we endow this A with this topology, and then instead of generating, we put dense, this X is dense in A?
I'm sorry, you're quite quiet. I can't quite hear you.
Okay. Is it possible to study this stuff with endowing with topology? For example, instead of generate, we put this X is a dense in A, something like that.
You can still, so axes are defined without generating. There is also a slightly more general setup than axial algebras called decomposition algebras. And there you don't require that the axes generate, or if you've got axes, that they actually generate the whole algebra. The problem that you get is, without this generation condition, I could just take an algebra and take, say, the direct sum with another algebra. And if all my axes lie in the first algebra, and I'm never going to see the second part of my algebra, I'm going to generate things in here, and I can do direct sum with as much stuff as you like. And because the product, those will always be in the zero part, I'm thinking of this direct sum as meaning it has product zero with the first part. So that's always going to be in the zero eigenspace with respect to the axes. And so you lose control over being able to multiply things.
Okay, thank you.
The axes. And so you lose control over being able to multiply things.
Okay, thank you. Other questions, please? So if no questions, thanks one more time to the presenter. So now we have a lunch break, 1 hour. So then we resume our second section. Okay, thank you for all. See you soon.
Bye-bye. Thank you. See you tomorrow.